Everyone, we want to do a couple examples here for problems with friction and showing you how to set up the problem, how to make sure you know whether to use mu s or mu k, depending on how the scenario is set up. What we got here is our scenario of two objects sliding off a hill. This can be similar to that Batman problem we did in class. I've given you the static coefficient and the kinetic coefficient. I've given you the masses and the angles. And the first thing you need to know is, are these two things actually going to slide? Are they actually going to go over the hill? So in that case, we need to look at our max static friction. And our max static friction is going to be mu times our normal force. So mu is already given to us. It's here as 0.5. So we're good there. We need to find the normal force. And the normal force is going to come from the only block that's in contact with anything and causing two surfaces to rub together. So we've got gravity on this one. We've got the support force right here. And I've got friction back. So those three forces there, that's what's kind of resisting things from trying to move, that frictional force backwards. So I need to find that angled normal force and how much that normal force is actually pushing. So if I break this up into x and y pieces, I can see that this y component's got to be equal to my normal force, and this x component is trying to push us down the hill. So to find the normal force here, looks like it's going to be mg cosine theta for block 1. There's no friction on block 2, not dealing with any drag right now. So inputting all your values, you end up with a max static friction force of about 43.3 newtons. The block 2 and the x component of block 1 are enough to pull harder than 43.3 newtons. This whole thing's going to go. So we need to analyze both of these and figure out which way this thing's going to accelerate. So if we break up our force diagrams into both blocks separately, we can see that block 2 is a really simple force diagram. Tension up, gravity down, we're accelerating downwards, so that weight must be bigger than whatever the tension is. So we can easily solve for tension here, and rearranging, the tension is going to be m2g minus m2a. So we're going to go over and look at block 1. Normal force is just in the y direction. The frictional force is just in the x direction. Gravity is one of those angled pieces, and tension is in the x direction. So when we look at all these, we know that the block 1 is going to accelerate in its horizontal direction up and over the hill. If that force can be stronger than the force of friction, the two forces that are down the hill are mg sine and tension, and the only thing fighting back up the hill is that frictional force. So as long as these two forces here, the tension and the mg sine, are bigger than that 43 newtons, we are going to start moving. And if we start moving, we're going to use the mu k value instead of the mu s, since the thing will not be static. Looking at those tensions, what you come over here to block 2 is say that this acceleration here is 0, and you put that over into block 1. So that means the two forces that are pulling down the hill are going to be the weight of block 2 and part of the weight of block 1. So crunching in your numbers from there, we've got 200 newtons for block 2 and 50 newtons for block 1. Adding those two together, you get 250 newtons pulling down the hill, which is much more than the 43 newtons of friction pulling backwards, so we know this thing's going to accelerate. Rearranging everything and putting our tension into our x direction, since we want to solve for the acceleration of this block, what we get is minus the force of friction, plus the mg sine theta of block 1 pushing down the hill, plus the tension, which is m2g minus m2a, and all that's going to make mass 1 accelerate. So if we want to get the MAs all together, what you got on one side is mass 1 plus mass 2 times acceleration, and on the left side of our formula here, we've got m2g plus m1g sine minus that force of friction, m1g cosine. So again, if we want to rearrange and solve for acceleration, we're going to divide all of those forces by the total mass of m1 plus m2. So the acceleration of the system here is the weight of block 2 plus part of the weight of block 1 minus the frictional force on block 1. Those are the three forces that are fighting each other, and you're dividing by total mass again. So it gets a little more complicated when you have. In our drag force lesson, I proposed to you a way to solve for the velocity as a function of time as your drag force increases. We said at the beginning there is no velocity, so you just freely fall and you jump out of the plane. And after a long time, you get those two forces, gravity and the drag, to equal out, and that's when we hit our terminal velocity and acceleration terminates. But in the in-between parts, like we saw in the coffee filter lab, there's a time it takes for you to reach that top speed. And if we wanted to solve for your velocity as time goes on while the drag force is increasing, we can set up a differential equation. So let's go back to that differential and show us how to set that up. So this is the setup we had for the drag force. We had the force of gravity down and we had the drag force up. It was not as strong as your force of gravity yet, so the force of drag is increasing as time goes on. And if you write out your forces, you get negative BV plus mg plus ma. And I'm taking the downward direction to be positive in this example. So what we wanted to do is, that is set up as a differential. We want to solve that differential for velocity as a function of time. And if you look, I've got a v on one side in the BV drag force, and I've got dv on the other side in the definition of acceleration. So we need to combine those terms so that we can actually solve for the things that we're looking for. So what we want to do is get the velocity all by itself. So the first thing we can do is divide by that negative b. If I divide this whole side by negative b, I've got to do the same thing to the other side of my formula. So in that rearrangement, you should get velocity equals negative mg over b equals negative m over b dv dt. Again, we need to get those velocities and that the v and the dv together and leave the dt to the other side. Doing some algebra, you should rearrange your equation and do this. If you're having trouble getting from this step to the next, come see me, but I'm going to skip a few steps here to get to my final integrated setup. So now our differential is set up, and I've separated the variables. I have my v's and dv's on one side, and I have dt on the other side. So what I'm going to have to do to solve for velocity is integrate both sides from 0 time until all time. And for our velocity function, we're going to start with our initial velocity of 0 until we reach some velocity v. Those are going to be the bounds of my integration. So we have to integrate both sides of this. Integrating the left side should be very easy. dt should just become negative b over m multiplied by t. On the other side, we've got dv over v minus a constant. If you look at that function, technically you have a 1 over x scenario for your integration. And if you have 1 over x becomes the natural log of just x. So this side of the formula should become natural log of that function. And we're going to evaluate that between those two bounds. So what that means is you need to throw in velocity for the first natural log and then 0 for the second natural log. Skipping a few steps, this is the natural log you should end up with. If you're having issues with this, please come let me know. I want to get rid of that natural log, so I've got to take e to both sides of my equation. And what that does is eliminate my natural log and leaves on the other side e to the negative b over mt. I'm going to solve for velocity, so I'm going to move that negative mg over b on the bottom. Now I'm going to solve for the velocity by getting rid of that constant on the left side of my formula. So looking at my final setup here, this is my velocity as a function of time as the drag force increases on me. So we can put some values in there and say what happens. So if I was going to graph our velocity as a function of time here, when we jump out of the plane, we are starting at 0 velocity. And when we reach terminal velocity after a long time, we're going to reach some constant speed. The question is, how do we get there? Let's say that time equals m over b. And by doing some of the equations in WebAssign, you can see that mass over this drag coefficient should give you a second in your units. So if I put that into my formula for t, this right up here becomes -1. So if I do e to the negative first, we get about 0.36. 1 minus 0.36 comes out to about 0.63. So after one value of this m over v, the velocity of the object is around 63% of its max. So at 63% of its max, it's going to go from 0 to about the 63% mark in one time period. If this becomes 2m over b, I get e to the minus 2 up top. And when I do e to the minus 2, subtracting the 1, I get about 0.86 of my maximum speed. So here I am at 63% of my maximum speed. In the next moment of time, I've reached up to 86% of my maximum speed. And after a few of these time constants, I eventually will reach this leveling off point of my steady speed. I'll get to the point where the steady speed is 100%. Eventually, the longer time goes, I can eliminate that e to the negative b over mt function, and you just get your maximum speed of mg over b. So this is how you set up a drag force equation or a differential equation in trying to solve for something as time goes on. The velocity changes every single second, which means the drag force changes every single second as well.